Yes, you're doing it while you listen to this, and some people have done it measurably faster. Sergei Krikalev spent 803 days, 9 hours, and 39 minutes off this planet across 6 flights, and Relativity puts him about a 50th of a second younger than everyone born the same day he was. Travel into the future is settled physics and dull enough that your phone leans on it. The atomic clocks aboard the GPS constellation gain 38.6 microseconds a day on hours, and uncorrected, your measured position would wander off by about 11 kilometers every day. So the honest answer comes in 2 halves. Forward is real, and we have the receipts. Backward is a different question, and the state of play there is uncomfortable. No known law of physics forbids it outright. No known mechanism makes it work. Start with the version you can check on a mountain. Muons are heavy relatives of the electron, made when cosmic rays hit the upper atmosphere, and left alone they fall apart in about 2.2 microseconds. That should buy them a few hundred meters. They shouldn't reach the ground at all. In 1962, David Frisch and James Smith counted them at the summit of Mount Washington, 1,917 meters up, and logged about 563 an hour. Then they counted again at sea level in Cambridge, Massachusetts. Without time dilation, 27 an hour should have survived the drop. They measured around 412. 15 years later, a team at CERN reported the cleaner version in Nature, whipping muons round a storage ring at a Lorentz factor of 29.327, and watching that 2.2 microsecond lifetime stretch to 64.378. Agreement with Einstein to 0.9 parts in 1,000. Speed isn't the only lever. Gravity slows clocks as well, and the effect has become so easy to detect that it's a nuisance for the people building better ones. In 2010, a group at NIST in Boulder took 2 aluminium-ion clocks, set them side by side, and raised one of them by 1/3 of a meter. The higher clock ran faster. 33 centimeters of altitude, and general relativity showed up in the data. 12 years on, Jun Ye's team at JILA went smaller. Writing in Nature, they resolved the same gravitational redshift across a single millimeter of ultracold strontium at a fractional uncertainty of 7.6 times 10 to the -21. So your head really is aging faster than your feet. That isn't a figure of speech anymore. Somebody has measured it a millimeter at a time. Which brings us back to the satellites, because GPS is where most people brush against relativity before breakfast. Each satellite sits about 20,000 kilometers up and travels at roughly 14,000 kilometers an hour. Its speed drags the onboard clock about 7.2 microseconds per day behind ours. Its altitude, out where Earth's pull is weaker, pushes it about 45.8 microseconds ahead. Net gain, 38.6 microseconds every day forever. A navigation fix is a stopwatch reading on a radio pulse, so the error walks straight into your position. Engineers solved it by cheating. Before launch, the oscillators are detuned, set to run at 10.22999999543 MHz rather than a clean 10.23, so that once they're up there they tick correctly for us. The fix is machined into the hardware. It has to be. So how much future can a person actually buy? Very little so far. Krikalev held the cumulative record for years before Gennady Padalka took it with 878 days. Oleg Kononenko has since passed both, crossing 1,000 days in space on 4 June 2024 and finishing his last mission with a total measured at 1,110 days, 14 hours and 57 minutes. Scale Krikalev's figure by the extra time aloft, and Kononenko lands about 3/100ths of a second out of step with the rest of us. That's the human record for time travel. A blink earned over 3 years of falling around the Earth. The physics scales without limit, though. Push a ship close enough to light speed, and its crew steps out into an Earth centuries older. The theory doesn't object. The fuel bill is what's absurd. Backwards is where it gets difficult, and it starts with a birthday present. In 1949, Kurt Gödel, Einstein's walking companion at Princeton, published a solution to the field equations in Reviews of Modern Physics, and by the usual telling, he handed it to Einstein as a gift for his 70th. It described a universe of rotating dust, with a negative cosmological constant and no expansion at all. Fly a wide enough loop through that universe, and you arrive before you set out. Not as an analogy, as a world line that closes on its own past. Physicists call them closed time-like curves, and Gödel had shown that Einstein's own equations allowed them. Einstein was gracious in print and plainly rattled, writing that the distinction between earlier and later gets abandoned and the paradoxes of causal direction arrive. We don't live there, though. Our universe expands and shows no trace of the rotation Gödel's model needs. Rotation keeps coming up. Roy Kaya published the exact solution for a spinning black hole in Physical Review Letters in 1963, and it's the geometry we think fits essentially every black hole in the sky. Follow its interior mathematics past the inner horizon, down towards the ring singularity, and closed time-like curves turn up again. So there may be a time machine buried inside every rotating black hole in the universe. But the catch is brutal. That region is an extrapolation of a perfectly smooth idealization, and it's violently unstable to anything that falls in. Real infalling matter should turn the inner horizon into a wall of diverging energy long before you get there. There's a road on the map. The road is probably not there. The most serious proposal owes a debt to a novelist. Carl Sagan needed a defensible way to move a character across the galaxy in Contact, and his friend Kip Thorne handed him the wormhole. Thorne and his graduate student Michael Morris then worked out what one would have to be for a human to survive it, and their 1988 paper in the American Journal of Physics is still the standard reference. Later that year, Morris, Thorne, and Ulvi Uetseva published the sequel in Physical Review Letters, and the sequel is the alarming one. Take a traversable wormhole, fly one mouth on a fast round trip, bring it home, and the two ends stop agreeing about what time it is. Walk in one side, step out of the other, and you've arrived before you left. Clean mathematics. Impossible shopping list. Holding the throat open demands matter with negative energy density, violating the null energy condition, and the only thing resembling it we've ever made is the Casimir effect between two plates in quantities close to nothing. There's an older scheme that skips wormholes and hits the same wall. Willem Jacob van Stockham solved the equations for a rotating cylinder of dust in 1936, and in 1974, Frank Tipler worked out what that solution permitted and published it in Physical Review D. Spin a dense enough cylinder fast enough, and it drags spacetime around with it, tilting the light cones until a path into the past opens along its length. Tipler's version needed the cylinder to be infinitely long. He suspected a finite one might do, he never proved it. Hawking argued later that it can't, and said so flatly, to build a finite time machine, you need negative energy. Same missing ingredient. And every route to the past anyone has found on paper eventually asks for a substance nobody has ever held. Hawking had already built that objection into a full conjecture. In 1992, he published Chronology Protection in Physical Review D, and the argument has a certain cruelty to it. As any device approaches the instant it would first permit a closed time-like curve, quantum vacuum fluctuations begin circulating around the loop, amplifying on each pass, and the energy density runs away at the boundary. The machine destroys itself at the exact moment it would start working. His summary has outlived the paper. It seems that there is a chronology protection agency, he wrote, which prevents the appearance of closed time-like curves and so makes the universe safe for historians. Lovely line. Not a proof. In 1997, K. Radzikowski and Wald showed in general that the semiclassical calculation blows up right at that horizon, which is precisely where semiclassical physics stops being trustworthy. Settling it needs quantum gravity, and nobody has quantum gravity. Suppose you got past all of it. What happens when the traveler shoots his own grandfather? Physics offers two serious answers, and they disagree about the shape of reality. Igor Novikov's is that the universe never permits an inconsistent history, so events that would create a paradox have probability 0. Novikov, Thorne, and their co-authors set out the formal version in Physical Review D in 1990, and the test case is wonderfully mundane. Joseph Polchinski imagined a billiard ball fired into a wormhole so that its older self comes back to knock it off course. Echeverria, Klinkhammer, and Thorne worked out the answer in Physical Review D in 1991. The ball takes a glancing blow from its future self, and that deflection is exactly what puts it on the trajectory to deliver the blow. Not one solution, infinitely many. The gun jams or the aim drifts, and the grandfather lives because the traveler came back to kill him. The other answer refuses the constraint entirely. David Deutsch worked the problem quantum mechanically in 1991, also in Physical Review D, and found self-consistent solutions with no mysterious veto hovering over your free will. The traveler arrives in a branch of the wave function where the killing simply happens, while the branch he left carries on with its grandfather intact. He kills a grandfather, just never his own. Alan Everett later objected that the model would smear a macroscopic traveler across parallel worlds, and Hawking preferred a single self-consistent history over an infinity of them. But none of it can be tested. That's the honest condition of the whole field. On 28 June 2009, Stephen Hawking threw a party for time travelers. He publicized it only after it had finished, so the only guests who could possibly have known to attend were people arriving from the future. Nobody came. He put that forward as a tongue-in-cheek test of his own conjecture, and it settles nothing, because a time machine can only carry you back as far as the moment it was switched on, and nobody has switched one on yet. That's roughly where the science stands. The future is open to anyone who can pay for the velocity, and the correction for it is already running in the receiver in your pocket. The past is guarded by a substance nobody has produced and a conjecture nobody has proved. Time travel isn't impossible. It's unbuilt. The distance between those two words is the whole remaining problem.